All right, so welcome everyone. It's a pleasure to have a new econometrics Chamberlain seminar. And to have Sophie soon, who is going to talk about adapting to misspecification. We also have the pleasure to have three panelists, so Cheng, Bruce Hansen, and Max Kasy. Sophie, you have around 1 hour, and we will also take if you have some questions, please write to me and through the chat, and I will either unmute you or read directly the questions and some moments where we will pause for such questions. So Sophie, the floor is yours.
Okay, thank you so much, Xavier, for the introduction. I'm Liyang. You can also call me Sophie. And this is a joint project with Tim Armstrong and Pat Klein. And we're very grateful for the opportunity to the organizers, the moderator, and our panelists for this opportunity to tell you what we have figured out so far for what's known as robustness checks that are common in applied micro research. So the context is that when we estimate a scalar target parameter theta, say the average effect of some policy intervention, we commonly see robustness exercises that would include a robust estimator that we call it YU. And by robust, we mean it's asymptotically unbiased under weak assumptions. And another estimator that we see in these robustness checks would be a restricted estimator YR that impose additional restrictions than the robust estimator for estimating theta. And if these additional restrictions are correct, then YR would turn out to be a more efficient estimator than YU. But if the restrictions are violated, then it would have an unknown asymptotic bias, call it small b. So how I got started working on the sub-questions is that from working on linear panel event study models, we now understand the canonical two-way fixed effects estimators imposes the restriction of treatment effect homogeneity. So if the homogeneity restriction is violated, then the canonical two-way fixed effects estimator would estimate a non-convex weighted average of the underlying treatment effects. So therefore, it can be biased for estimating a natural average of the underlying treatment effects if there is a lot of treatment effect heterogeneity. But in recent literature, there are robust estimators proposed in replacing these restricted estimator. So those would correspond to the YU in our setting. And here I show you a table from Xavier and Clement's 2020 paper where they report both the original two-way fixed effects estimates for the particular target parameter in this case, as well as the estimate based on the robust estimators. So the goal of our paper is to summarize robustness checks as you would see in tables as such. And to do that, we propose a new way to combine YU and YR into a single estimator. And the single estimator would have the property of being optimally adaptive that I'll explain later. But for now, we think our proposal has a broad usage in applied research because this type of concern of choosing between YU and YR can arise more generally whenever YR is based on some over-identifying restrictions. So if we take the difference between YR and YU and call it YO, this is a noisy estimate for the potential bias in YR that's due to potential misspecification of the over-identifying restrictions. And formally, if we take the framework of local misspecification, so here YU and YO have the root and scaling embedded. So we take the nuisance parameter, which is the bias here, to be not consistently estimable. Most of our examples are actually based on linear models. So this asymptotic approximation is also valid globally. And for nonlinear models, this can be considered as the approximation based on the first order asymptotic bias. So this local misspecification framework is useful because it encompasses the over ID test based on the standardized YO, which we call TO as the over identification test statistic. This is also sometimes referred to as a Hausman test if the restricted estimator YR turns out to be the most efficient estimator when there's really no bias. But we don't restrict ourselves to the Hausman setting. Specifically, if we look at the asymptotic variance covariance matrix between YU and YO, which we also take to be consistently estimable, there's no restriction placed on the off-diagonal terms. But as it will turn out later, it will be useful to reparameterize sigma in terms of the correlation coefficient rho here, which you can think of as roughly measuring how much more inefficient YU is relative to YR if there is no bias. So our proposal in the paper is not to use TO to test for potential misspecification in YR, but rather to use TO as a way to combine YU and YR into a single estimate. Let me provide a quick overview of our logic and develop further ideas along the talk. So let's consider how we might perform estimation for the target parameter theta as we get less and less certain about the actual bias in the restricted estimator YR. So in the first scenario, suppose we're very certain what the bias is. Then in this case, if we focus on the mean squared error, we can just use the GMM that imposes the restriction that the recentered YR should estimate the same target parameter as the robust estimator YU and combine them into a single GMM estimator that's the most efficient one. Suppose we get less certain about the actual bias, but still have enough prior information to place a bound on the bias and call it capital B. So this is a upper bound on the magnitude of the bias. Then for each bias space where the true bias belongs to the minus capital B to capital B interval, it will be natural to consider an estimator that minimizes the worst case risk over this bias space. We call these estimators the B minimax estimators to highlight that their minimax optimality hinges on the bias space we're talking about. And we also use R star phi to denote their minimax risk by achieved by these B minimax estimators. To make things a bit more concrete, I'm going to show you the running example in our paper, which is based on a 2018 empirical study by Dopkins and co-authors that estimates the effect of hospitalization on medical spending using parallel trends type of assumptions. So here's a plot from the original paper. And for illustration's purpose, we can think of the robust estimator YU here as the one that allows for a potential linear violation to the parallel trends. So that would allow for a linear pre-trend as shown here. The restricted estimator imposes the parallel trends assumption exactly. So imposes that there's no pre-trend leading up to hospitalization. And it would also be more precise than the robust estimator when parallel trends assumption hold exactly. And in fact, we can do even better by combining them into an GMM estimator, as I show here on the left vertical axis, which gives a larger estimate for the impact of hospitalization than the robust estimate. This GMM estimator also has a substantial risk reduction compared to the robust estimator if the bias is indeed zero, which you can read off the right vertical axis, where the risk is normalized relative to the robust estimator. If we're less certain whether parallel trends assumption hold exactly and think there might be some bias in the zero pre-trend estimator, But we might think that this bias cannot be too large. For example, place a bound that the bias cannot be more than 1 standard error away from 0. Then we can report the corresponding B minimax estimate, which is shown here in this triangle. And we can also calculate its corresponding minimax risk here, which I plot in the orange dashed curve that tracks the minimax risk as we vary the upper bound on the bias. So as the upper bound tends to infinity, this would converge to just the risk of the robust estimator, because the robust estimator is the minimax estimator if there's no restriction on what the bias could be. But to achieve the risk as shown here in the orange curve, it requires the knowledge of what the upper bound actually is. So that's why we call this risk function the oracle risk function, because it uses the knowledge of what upper bound we're discussing to switch among the collection of these B minimax estimates as shown in the triangles. So in the situation where we do not have information about the upper bound on the bias and want to rely on a single estimator without specifying the upper bound on the bias, that is what our proposal of doing adaptation comes in, to use an estimator that mimic the oracle risk performance. So how well can a single estimator mimic the oracle that can switches among the collection of different B minimax estimators using the knowledge of the actual upper bound? So of course, at each given upper bound, this single estimator delta would incur a risk increase relative to the oracle. And this is what we call the adaptation regret, which is the ratio of the worst case risk of this estimator delta evaluated on the corresponding bias space relative to the oracle risk. So this reflects the regret because it comes from using a single estimator to adapt to different bias spaces, as opposed to being able to switch to the relevant B minimax estimators depending on what the capital B is. And our proposal for the single estimator in situations as such is to use the optimally adaptive estimator that minimizes the worst case adaptation regret over a collection of bias spaces that we care about. So in the setting, all possible upper bounds that we're willing to consider. So in the running example, if we look at the risk function of our proposed adaptive estimator, as shown here in the orange dotted line, it hovers just above the oracle risk function to minimize the worst case deviation from the oracle performance. But this is actually achieved by a single estimator without specifying what the upper bound is. And for this particular running example, the adaptive estimator would return an estimate that's halfway between YU and YR. But as I will explain later, the weight placed on YU and YR is actually data dependent and also depends on how much more inefficient is YU relative to YR when there's no bias. So this is the overview of our proposal. And in terms of how our paper is related to the stats literature, of course, there's, oh, I see Max raised a hand. Should I take question now or?
Yes, you can, yes. Yeah.
Oh, okay. Oh, can you hear me, Max? Oh, we cannot hear you, or at least I cannot hear you.
I cannot either.
How about now? Hello?
Oh,
Yes.
now it's better.
Yes.
Great, thank you.
Sorry about that. I just wanted to ask a quick intuition question about the previous picture. I see that the adaptive risk does not go, the relative risk relative to YU does not go down to YU. And I found it surprising, like with an intuition from like a pretest estimator, I would have thought once the bias gets large, I can figure out that the restricted estimator is wrong, and therefore I just use the unrestricted estimator effectively. So why does the mean squared error not go down to 1 or stay near 1?
So in general, it will not go down to 1, and that is exactly because it actually focuses on different property than the pretest. It's actually looking at the worst case deviation. So it actually balances the deviation from the oracle also when the bias is 0, as well as when the bias is very large. So that's an intuition for why it doesn't go down to 1 exactly. And actually later I will show you exactly the comparison with the pretest estimator, in the sense that while pretest would be attractive if the bias is also very small or very large, it's actually not so attractive for the intermediate range of the upper bound of the bias. So yeah, it's exactly because the property our proposed adaptive estimator is trying to optimize, it doesn't tend to 1.
Thank you.
So let me just quickly go on to the literature review and also pause after that for more questions. So in terms of how our proposal relates to the stats literature, there is a large literature from high dimensional statistics about the adaptive choice of tuning parameters. And here the definition of adaptation also comes from statistics, where in the 1998 paper by Tsipakov, he proposed to define a procedure to be adaptive over a set of parameter spaces, which would correspond to different bias spaces in our example, if the procedure is simultaneously achieving near minimax risk for all of these parameter spaces. In the high dimensional stats literature, adaptation is usually considered in terms of the optimal rate, as well as for choosing tuning parameters. And for us, we focus on a low dimensional setting, estimating a scalar parameter, and we also focus on adaptation results, the exact adaptation results. And the exception from the stats literature is a 1984 paper by Peter Bickel that considers exactly the adaptive estimation for a scalar parameter when adapting to just 2 bias spaces when either bias is 0 or when the bias belongs to the real line. And our paper improves upon this paper to adapt to the intermediate bias spaces where the upper bound on the bias can take on intermediate values between 0 and infinity. And for the relation to the econometrics literature, our paper is related to the specification testing literature, as well as model selection and averaging that Cheng, Bruce Hansen, and Max Kasy have all worked on. And more recently, Clement and Xavier have a working paper that's mostly closely related to our setting that considers model averaging for estimating a scalar parameter. One of the reasons we focus on adaptive estimation for a scalar parameter is that doing adaptive inference is not possible, as shown in the recent paper, in the classical sense of maintaining uniform coverage. And finally, the way we solve these adaptive estimation problem builds on the literature that converts minimax problem to solving for the least favorable prior problems, as illustrated here in an early 2000 paper by Gary Chamberlain that we borrow ideas from extensively. So I think this is a natural stopping point to collect questions.
So in this paper, you only cover the scalar case, right? You don't do the higher dimensional case, which presumably would look more like James-Stein shrinkage or similar types of estimators, right?
Right. Only the low dimension, very low dimensional scalar case, yes. Yeah, so the later shrinkage you see would not come from Stein's type of arguments. I see Xu had a question.
Yeah, I just have a quick clarification question related to the figure you show in the last slide. Over there, you have starting point, you have this restricted and unrestricted estimator, but obviously here is the GMM, which is also biased. I just wonder, does it matter as a starting point which estimator is called the restricted estimator? I use to construct this adaptive estimation? For example, why can't I just use this GMM as the restricted estimator as a starting point?
Oh, yes, of course, you can use the GMM as starting point just to be more empirically relevant, that not all the restricted estimator reported in papers are the most efficient, although most cases they are very close to the most efficient GMM. So doing GMM would not improve the efficiency much more. In a lot of empirical examples we revisited, but there are cases that we can still improve. Imposing the bias is 0. But of course, once bias is non-zero, both are biased, yes.
Just in the end, so the final adaptive results, is that sensitive, or does that matter which one is the restricted estimator to use in the initial construction? Or it doesn't really matter in the end which one I use, like some combinations of the original restricted estimator and yes, there are different versions of that biased estimator.
Oh yeah, it doesn't really matter because in the end, we'll see the adaptive estimator takes on the form that adjusts the GMM estimator as a starting point. So even if we start with the restricted estimator, we end up building upon the GMM estimator for adaptation. So it doesn't quite matter. All it matters is the relative efficiency trade-off at 0 between YU and YR, which was also reflected in the GMM. So yeah, it doesn't quite matter. But we just thought this would be a more general framework to start with.
If I might jump in, do I understand right from this picture that for the dotted line, that the adaptive risk, that your adaptive estimator is not minimax?
It's not minimax in the canonical sense, where it's the robust estimator that's minimax if we allow for restricted bias space, but it's minimizing the worst case regret. So it's minimax in another interpretation, but no, it's not minimax. It's not the robust estimator.
Okay, yeah, you have not yet introduced the regret criterion, so maybe let's go forward.
Yes, that will come up. Great, so thanks so much for all these very helpful questions, and I will move on to cover the general setup and then build on to how we define the regret. So this is a framework where the data is YU and YR, but we can more easily reparameterize in terms of the difference between YR and YU, called YO. And the data is distributed according to unknown parameters. So that includes both the target parameter theta as well as the nuisance parameter B, which stands for bias. If we look at a estimator, which can be viewed as a decision that maps the observed data into an estimate or an action, then the loss function measures the disutility of relying on the estimate when the true parameters are theta and B. And the risk function of this estimator, delta, is the expected loss under the true parameters. And because we focus on squared error loss in our paper, the implied risk function is given by the mean squared error. So now suppose a researcher has no prior information about the target parameter, so theta can belong to the real line, but instead might have some information about the magnitude of the bias. So even though we cannot pinpoint the exact value of the bias, but we might have enough information to pinpoint the upper bound. Then consider a researcher that entertains the multiple bias spaces that are here nested and indexed by the upper bound that the researcher places on the bias. And these bias subspaces can also be collected into the collection of possible upper bounds that we allow to range from 0 to infinity. Then for any given parameter space, we are interested in the worst case risk of the estimator, which we use Rmax to denote this quantity. That searches over all possible bias belongs to the corresponding interval. then it will be reasonable to use a minimax estimator that minimizes the worst case risk within this corresponding bias space. And to be specific about how these minimax estimators are indexed by the bias spaces, we call them the B minimax estimators. And their obtained optimized minimax risk is denoted to be R star of B. So for example, when the upper bound is imposed to be 0, the B minimax estimator is the GMM under the mean squared error criterion. And this point I've already discussed earlier. If upper bound is infinity, that bias is unrestricted, then the minimax estimator is the robust estimator, because we have to throw out the restricted estimator, which would have unbounded worst case risk. So the choice between the upper bound would reflect the trade-offs between efficiency against robustness. And we can look at sensitivity analysis that reports these B minimax estimates as we vary the upper bound for reasonable ranges of the upper bound. So that's exactly the plot of the triangles I presented at the beginning of the talk. And I'll come back to how to compute these B minimax estimators for intermediate values in a little bit. So this slide is the key idea of our paper to Bruce's question, in the sense that we want to commit to a single estimator rather than reporting the sensitivity analysis that relies on the collection of B minimax estimates. So because we rely on a single estimator, we would of course incur some increase in the worst case risk compared to the oracle that can switch between B minimax estimators and achieve the minimax risk. And we can't quantify this cost based on what we call the adaptation regret, which is the at any given upper bound B, the ratio between the worst case risk of the candidate at estimator delta relative to the oracle risk. So this is the regret from committing to a single estimator because at any given upper bound, this estimator would always underperform compared to the oracle. Max, do you want to ask the question now?
Yeah, does it matter that you define regret as the ratio here rather than a difference, which I guess would be more common?
Oh, it actually matters to define in terms of the ratio. So firstly, that kills the unit. And also it's in the ratio that we really see how adaptation can be reflective of the original efficiency trade-off between YU and YR. So at least as the leading case, we want to define adaptation regret as the ratio. And we can consider difference as an extension. But we think this ratio is more natural and also matches with what the stats literature is considering as well. So with this definition for adaptation regret, our proposed single estimator is the optimally adaptive estimator, delta adapt, that minimizes the worst case adaptation regret. So to Bruce's question, this is a minimax in a sense, but not quite minimax because it's about minimizing the worst case adaptation regret. This quantity, the minimized quantity called A star, which is a function of the collection of bias spaces that we want to adapt to. If this quantity is small, say close to 1, then we call the optimally adaptive estimator near minimax, because there is very little loss of efficiency under adapting to a collection of bias spaces. It might seem difficult to compute this optimally adaptive estimator at first glance, which involves swooping over a collection of infinitely many bias spaces indexed by their upper bound. And after that, we need to compute the minimax risk. But as I will show you on this slide, the adaptation problem, which is minimizing the worst case adaptation regret, can be actually rewritten as a weighted minimax problem with a particular weighting scheme. So we have more details in the paper, but for the framework of local misspecification, where the bias spaces are nested and the minimax risk increases in the upper bound, the formula for the weight turns out very nicely, which would be equal to the inverse of the minimax risk evaluated at the absolute value of each of the value of the bias that we're searching over in the weighted minimax problem. So this means if we have a general procedure for computing the minimax problem that involves for solving for the B minimax estimator as well as for getting these oracle risk functions, then we can use the same procedure for solving minimax problem to solve the adaptation problem, though on the surface it's solving a different problem by minimizing the worst case adaptation regrets. Under the hood, effectively, it boils down to solving a weighted minimax problem. So this simplifies the computation by a lot. So I think this is also a natural stopping point in case there are questions about this adaptation framework.
Yes, so I have a question myself and also a question from the audience. So the question is whether here it looks a bit like a mix between like standard minimax and something which would have a flavor of a Bayesian procedure, right? Because you have these weights, so the omega looks a bit like as if you had a kind of prior on theta and B. So I don't know whether you elaborate on this in the paper, whether you have some thoughts. Maybe it doesn't make any sense actually.
Oh yeah, thanks for the pointing out of the connection. So it looks like a Bayesian approach that there are different weights placed on the values of the bias, and in particular, this would put more weight on smaller values of the bias because the minimax risk would be smaller, but it comes from putting equal weight on different bias spaces. So in that case, it's not relying on prior information on which upper bound of the bias is more likely. So in that sense, we'll try to say that we're not Bayesian without relying on any prior information, although mechanically it would look like we're solving a minimax problem with a weighting scheme, and to preview a little bit, we would also get a solution that looks like a least favorable prior, but the starting point is try to be prior free. I'm also happy to take the audience's question.
Yes, okay, thank you. And so let me see if I so maybe I'll read the question. It will be more efficient this way. So it's a question by Andrei Zrakar about bias spaces, given that these bias spaces may be a bit a bit complicated. So are they so the question is, are they necessarily Euclidean, for instance? Could they be manifolds and of different types? Also, how is the choice of GMM estimator motivated? Could any other estimator be chosen here?
So okay, let me unpack. I think it might be easier to go from the second question that we start with estimator that we can impose the local misspecification framework on, and this already covers most of the applied micro examples we looked at that have linear models. So under this framework, it's very general to then go on to the GMM estimator, since we also care about mean squared error. And then in this notation, it looks like we're looking at a scalar bias, but the results actually extend much more generally to a vector of the bias. So the bias space doesn't have to be a bounded interval, and the framework generalized, but computation is just much easier for the one-dimensional case. But I will have an example that illustrates a vector of bias spaces.
Okay, thank you.
I also have a question.
Yes.
I was looking at the adaptation formula before. So on the one hand, you don't want to impose information on the bound of this B. On the other hand, you do want to do the adaptation so that this is better than without any information on B. So it seems that this information about B is incorporated through this denominator R star B, right? So that seems to be like the estimator in the end would be adapting and changing with B is all through this, this denominator, that information over there. And in the end, I guess in your next slide, that'll be translated into the weight omega. That would be this thing is different for different weights across different capital B for a given lowercase b. I was just wondering, on the one hand, I'm trying to see if this is a way to incorporate this useful information on this capital B. On the other hand, I guess I want to understand more why this is a valuable or useful way to adapt to get information inside of the problem on this B. And why would this particular way to incorporate the information give us something that is near optimal in some sense? Why that's the best way to do that? I guess if we don't want to incorporate anything about the information of B, then without this R star, given that this B could be a nested parameter space, then that would be just becoming a B infinity problem.
Yes, yes, it will become a problem that would recover the robust estimator. So yes, I totally see your point, and thanks so much for working through the argument. I'm
just trying to understand a bit more about that ratio, I guess, the information it gives. Thank you.
Yeah. Yes, exactly, because we're making our reference to the oracle risk, which we are already making the reference to the oracle that knows the upper bound, not the oracle that knows the exact magnitude of the B. So after we take the stance that we want to adapt to the oracle that knows the upper bound and not the oracle that knows the true bias, then this is how we have the minimax risk showing up in the ratio to incorporate the incentive to adapt to a collection of bias spaces, not to adapt to just different values of bias, which would not be so successful because that would just degenerate to the robust estimator. But if we're adapting to the oracle that knows the upper bound, we can actually do more and would also be more interpretable to really showcase the efficiency trade-off between the robust and the GMM estimator when bias is small versus large. So I think I will probably proceed, but happy to discuss more, Xu, about this point, because I think this is the key idea of our paper, to really argue why adapting to the oracle that knows the bias spaces is more reasonable than adapting to oracle that knows the exact bias.
Yeah, thank you for the explanation. I did not follow up because I thought that was very helpful. And it was a very vague question.
Oh, okay.
I don't even know how to clearly remake myself to start with. Thank you very much for that.
Oh, no, thank you so much for the question, and I'm happy to discuss more. So if there's no more question from the audience, I will go on to explain how we can actually solve the adaptation problem for minimizing the worst case adaptation regret. So as I explained, with some reordering, we are able to rewrite the adaptation problem as a minimax problem with a particular weighting scheme. So here is just reviewing the general procedure for solving minimax problem, which usually translates to solving for the least favorable prior. And to do that, I'm going to introduce just a little bit more notation, if you can bear with me. So here the base risk for a candidate estimator under a given prior is the integrated risk against the prior, where again, the risk is the expected loss. And if we take gamma to be the set of priors that are supported on the parameter space that we care about, then the space risk would provide a lower bound for the minimax risk. And if we can appeal to some minimax theorem, this lower bound becomes sharp and we can interchange the mean with the max. So turns the minimax problem to solving for the least favorable prior. Since we focus on squared error loss, the inner minimization is fairly easy. The optimal estimator is just the posterior mean. And the outer maximization now is concave in the prior coming from a convex set. So once we discretize the support of the prior into a fine grid, we can solve this problem by convex optimization routine. And this is exactly done in the 2000 paper by Chamberlain. And right now, it might still seem that we have to discretize both the prior for the target parameter as well as the nuisance parameter bias B, which could still be cumbersome. But for the case of squared error loss function, we're able to use invariant arguments to further simplify the problem. So here by invariance, I just mean that adding the constant to the parameter, target parameter, as well as to the estimate does not affect the loss. And the invariance argument implies that the solutions to the minimax problem have to take the form that's additively separable in the robust estimator. And therefore, the risk of this class of estimators does not depend on theta. So we just have to search for the least favorable prior over the nuisance parameter B only. And with the squared error loss, we can do some further simplification. And this shows that the B minimax estimators has to take the form that's additively separable in the GMM estimator that imposes zero bias, together with an adjustment term for the potential bias in the GMM estimator once the bias is no longer zero. So the adjustment is based on the over ID test statistic. And to map the original B minimax problem, here we are trying to solve a standardized minimax problem that's known as bounded normal means problem in statistics. That's about minimax estimation for the unknown mean for a standard normal, where we know the upper bound for the magnitude of the mean. So to translate the original B minimax problem to this standardized bounded normal means problem, we just standardize the original bound on the bias. And to approximate infinity here, we measure that as 9 standard error away from 0 to make our problem tractable. So since we have argued that solving the adaptation problem that minimizes the worst case adaptation regret is equivalent to solving a weighted minimax problem, all the invariance arguments as well as the simplification carried on. So the optimally adaptive estimator would also take on an additively separable form that starts from the GMM estimator together with a standardized adaptation problem that depends on the over ID test statistic, but also the correlation coefficient that measures how much more inefficient is the robust estimator relative to GMM when there is really no bias. So this is how we actually solve for the adaptation problem that involves applying a minimax theorem, discretize the support for the standardized bias. And mechanically, it's the same thing as solving for the least favorable prior, but these are not quite the same object, and therefore we give them the name adaptive priors, which I show here in the blue lines. So here, horizontal axis is the standardized bias. And the set of the red lines correspond to the actual least favorable prior that correspond to 2 B minimax problems. So as is well known, when the bound is very small, the least favorable prior just places 2 mass points on the endpoints. And the adaptive priors take on a similar discrete form, but places weight also on large bias. And that is how, even when the true bias is large, the adaptive estimator would have bounded risk. And we say this is an attractive property of these adaptive priors, even though they don't quite have the same interpretation as these favorable prior. So the exact form of these adaptive estimator can be a little bit complicated, but in general, we can write them as a weighted average between YU, the robust estimator, and the GMM estimator. So the weight will depend on the over ID test statistic, and overall it shrinks YU toward GMM, although here the motivation for shrinkage is different from Stein's estimator, but rather that we want to adapt to different bias spaces. And the pattern of the shrinkage would depend on the correlation coefficient only, thanks to our invariance argument. So we can tabulate these adaptive estimators for a fine grid of the correlation coefficient and store them in the lookup table for easy empirical access that just needs interpolation across correlation coefficients. So the exact shrinkage pattern can be a little complicated, as I show you in 2 slides. So we also thought of approximating the fully optimally adaptive estimator using the soft thresholding estimator that replaces the adjustment term here with a self-thresholding estimator for the bias the standardized bias based on the over ID test statistic. So shrinks all the way to 0 if the over ID test statistic is small, but otherwise just shaves off a little bit, where we also optimize the threshold to minimize the worst case adaptation regret. So this threshold can also depend on the correlation coefficients. And another comparison that we're going to make, referring to Max's question in the beginning, is the comparison with the pre-test estimator that we can model as a hard thresholding estimator that shrinks the bias to 0 once the observed over ID test statistic is below the critical value. And this threshold will not depend on the correlation coefficient. So for a particular correlation value of the correlation coefficient, which is the case for the running example, I can show you what these estimators look like. So on the horizontal axis, I have the support for the over ID test statistic, and the robust estimator would involve no shrinkage. So that's the blue 45-degree line. The adaptive estimator shrinks towards 0 and less so when the observed TO is large. And in contrast, the pretest would shrink a wide range of TOs to 0. The self-thresholding approximation to the fully adaptive estimator is somewhere in between. So this can also be compared based on their risk performance. So here the horizontal axis is the standardized bias, and we normalize the risk function relative to the robust estimator. So it's constant at 1 for the robust estimator, which is an attractive property. But if we think of situations where bias might be 0, then we are leaving a lot of efficiency gains on the table. And our adaptive estimator, together with the self-thresholding approximation, are able to reduce the risk when bias is actually small, but not incurring a very large worst case risk when bias is actually large. So this is in contrast to relying on the GMM or restricted estimator that would quickly have unbounded risk when the actual risk, actual bias is large. So I want to, oh yes, Max.
So I like this picture a lot, but I guess in a way it tells us that none of these estimators dominate each other, except that the soft threshold almost dominates your adaptive estimator, right? So in a way, which of those prefers, in some sense, I guess, putting on a Bayesian hat, the matter of where I believe the bias is likely to be, but there is no sense in which any one of them is uniformly preferred to the others in the same way we would have for the Chim-Stein setting.
No, yeah, there's no minimax property here as in Stein's setting, because we're talking about estimating a scalar parameter. So nothing dominates each other. I mean, the one that's oracle here cannot be achieved by a single estimator. So that's not achievable by any of these estimators. But if we're talking about the worst case adaptation regret as a property, then the optimal one is the fully adaptive one, and the self-thresholding is very close approximation. And in that aspect, the pretest is actually not doing so well, even though for very small bias and very large bias, it has attractive properties. But in the intermediate range, for example, if we observe a over ID that's 1.7, then we might end up in regions where there is a lot of regrets compared to the oracle. So in that sense, we can improve the pretest by firstly smoothing out the indicator function to do self-thresholding, and then further optimize the threshold to minimize the worst case deviation from the oracle. So that's how we got from the blue dashed line to the yellow risk function for the self-thresholding estimator. So
there is another question. So let me unmute Andrei.
Okay. Yes.
I think Andrei, can you talk now? Otherwise, I will read his question. Maybe I don't do the proper thing. So let me read his question anyway. So these were about. So okay. I cannot unmute apparently. About adaptive Bayesian priors. So I'm not sure I fully get it, but let me read it anyway. So could anything be more specific be said about these adaptive Bayesian priors? I think you mentioned they could be improper. Could they, for instance, be non-parametric Gaussian or Dirichlet processes? How extendable is the Bayesian framework here?
I see. No, so it's not a Bayesian prior. We don't come from a Bayesian problem. It's just that the techniques for solving looks like we're solving a least favorable prior, but these don't carry any interpretation as a prior. Mechanically, it places weight on the large bias so that we can control the worst case risk increase, but it's not a prior.
Thanks.
Yeah. So let me quickly go through the rest of the results. So firstly, for fixed correlation coefficient, we can solve for the adaptation problem. And we can also show that the worst case adaptation regret would increase to infinity as the correlation coefficient gets close to 1, which is equivalent to saying that the restricted estimator is very precise to the point that it's a number. So the growth rate is at a log rate, and this is also achieved by the self-thresholding estimator, which confirms how these two estimators have very similar behavior. And in the regions where the correlation coefficient is close to 1, as I mentioned, this is where the efficiency loss for a robust estimator is very large. Doing full adaptation could incur a unbounded worst case risk as well. So for these settings, we consider a partial adaptation that directly places a constraint on the worst case risk increase relative to the robust estimator, say no more than 20%. And we can also rewrite this constraint adaptation problem as a weighted minimax problem. So all the techniques for solving these constraint adaptation problem can carried on. And we also have a lookup table for this constraint version. So in practice, we can see if we switch to the constraint adaptive estimator, then it limits the worst case risk increase at the expense of somewhat smaller best case risk reduction. But over all possible ranges, the best case risk reduction is still much larger than the worst case risk increase. So this is actually the property that Clement and Xavier had in their working paper, even though we're looking at a different set of estimators. And finally, I'm going to cover the empirical exercises in our paper. So I think I probably should go on and take questions after I finish the last section, if that's okay. Okay, so the first example is to just close the loop of the running example that estimates the impact of hospitalization on medical spending that relies on parallel trends type of assumptions. And in particular, there are several horizons of estimates for this empirical study, and the difference between the robust and the restricted estimate widened over time. And our adaptive estimator ex post is halfway between, whereas the pretest would pick the restricted estimator always. So this is also a situation where doing constrained adaptation could be helpful because for the later horizons, the robust estimator turns out very inefficient relative to the GMM. So we can effectively clamp down the worst case risk increase for the fully adaptive estimator to be no more than 20%, as I show here. The other example that I also want to quickly cover is to close the loop of the example I mentioned in the beginning about two fixed effects estimator that can be potentially biased when there's heterogeneous treatment effects. So here the robust estimator would, we take it as the one proposed by Clement and Xavier in their 2020 paper. And if we rely on the robust estimator, we would incur a large worst case adaptation regret because there is a way to combine the robust estimator with a canonical fixed effects estimator to reach a much more precise GMM estimate. But we can also do this in a more principled way by using adaptive estimator that again is roughly halfway between robust and restricted estimator, and not with a very large worst case adaptation regret, so still close to the oracle performance. And the final example is to the previous question about adapting to higher dimensional restricted estimators. So this is a classical study by Lalonde. Originally was trying to assess whether we can use regression adjustments to correct quasi-experimental estimates to match with the RCT estimates. Here, our goal is a little bit different in the sense that we try to assess we can adapt to a different amount of selection bias in using different quasi-experimental control units. So here, YU, the robust estimator, is the one that's based on the RCT, and the first restricted estimator based on all available control units, and YR2 is based on a screened set of control units that already exclude very dissimilar units. And for illustration purpose, we are just going to adapt to 3 bias spaces that incorporate the intuition that YR2 is less biased. So here, YU again is very much noisy compared to what we could have gotten if there is really no bias compared to the GMM3 that combines all 3 estimators. But the J-test actually rejects here because YR1 is very different from the robust estimates. And the adaptive estimator we propose ex post will look similar to the GMM2 estimator that combines YU and YR2. But it's under a completely different principle that tries to get close to the oracle that's able to switch across these 3 bias spaces and switch to the corresponding minimax estimators. So in that regard, the adaptive estimator also improves upon the pretest estimator by lowering the worst case adaptation regret. So let me conclude and then perhaps take on more questions. So this is a paper that tries to address the scenario where applied researchers often estimate a sequence of nested specifications. Oh, yes, Rabia.
No, but let you finish. I let you finish the conclusion, and then I'll ask the question. It was just to to be sure that I will ask it at some point.
Oh, sorry, just didn't want to forget the question. So yeah, let me quickly conclude and take your question. So this is about robustness checks that are very common in applied micro research that reports estimates from a sequence of nested specifications. And we recognize that this is the classical robustness efficiency trade-off. And in particular, we're able to allow the trade-off based on a continuum of models indexed by different degrees of misspecification. And our proposal is based on a single estimator that we call the optimally adaptive estimator that uses the over ID test statistic not to select specification, but rather to combine these estimates into a single estimate that minimizes the worst case adaptation regret. So hopefully this proposal is somewhat useful to apply researchers, and we pre-tabulate the solutions in MATLAB and R code, and hopefully soon data in this repository online. So thank you so much for all the questions so far, and look forward to more discussions.
So yes, thank you very much, Sophie. So the question I had was related to inference. Do you have any idea on how to perform inference based on this estimator? Have you thought about that? Huh?
Yeah, so inference in the classical sense of controlling uniform coverage is not able to improve more compared to the minimax confidence interval. So that would just be the confidence interval based on the robust estimate. So for that, we don't have more to say. But if we are willing to redefine inference based on different criteria, then there might be room for improvement. Yeah, so yes, not much to say yet.
Maybe there could be some way where we somewhat relax uniformity, the uniformity requirement, no? So usually uniformity would be okay. I take the worst case scenario and I try to control over this worst case scenario, but maybe under some weakening version of this condition, there would be some way to exploit the estimator to do better than just use YU. No?
I see. Yeah, I think we would have to redefine the objective that we want to optimize to do adaptive inference. Yeah, so I agree. Something has to go.
Do you have any sense how your shrinkage factors would behave in like higher dimensions? I guess sorry, getting back to my fixation on James Stein, but say if you're like in dimension 3 or higher, what would happen to like the trade-off between the restricted estimate? Or have you only worked out the one-dimensional case?
Yeah, that's a good question. So harder and harder to visualize, and I guess I just want to clarify that even though in the end we are able to do higher dimensional restricted estimator, we're still estimating the same target parameter. So the shrinkage is about shrinking the observed over ID tested statistic towards 0. So if we are in a higher dimensional case for TO, the shrinkage would be different, and that would really depend on the bias spaces we're adapting to. So in the example where we think the second restricted estimator is more likely to be unbiased, it will shrink a little bit more aggressively in that dimension. But in the end, I don't expect this would look exactly like Shine's shrinkage pattern because we're estimating a scalar parameter. I think, did I see Bruce raised your hand?
Yeah, and this is less of a question than perhaps a statement, that it seems to me that part of you said this at one point in the paper, your presentation, that the core idea is really focusing on this adaptive regret concept. And I think this might be kind of the linchpin of our understanding about whether or not this is the way we want to go or not. I think many of us have a love-hate relationship with regret, that sometimes regret's kind of a concept that's hard to justify from on principle, but often delivers things that seem right. And so in other words, is it really the case that someone says, oh, what I want to do is do the best estimation, given that I know that the bias is in this region, and et cetera. It's somewhat unnatural. And I'll just kind of leave it at that. And just this is going to be, I think, a challenge.
I see, in the sense that it's harder to justify why we want to adapt to an oracle that knows the bias basis. Or you're more asking for why we're taking the ratio here?
Well, both. So it's true that, like I say, that I think most of us realize that when we work with regret, we've used it as a tool that ends up delivering something which feels right. There's somewhat of this looseness in how we end up using this tool. And at the end of the day does it work? And in some sense, what you do at the end feels right, that you're doing this soft thresholding. Yet, I mean, anyway, but it's a core issue of the justification.
I see. Yeah, I see. It's definitely true that this would prevent us from getting back to the robust estimator. But I think our argument is that this is the way for us to really illustrate the efficiency robustness trade-off more saliently. So for example, taking the ratio would actually allow the shrinkage to depend on the correlation coefficient. If we actually define the regret based on the difference, it actually is a much weaker way to penalize situation that we leave efficiency gain on the table. So using the additive form of regret, we still end up with a shrinkage estimator, but the pattern of shrinkage doesn't depend on the correlation coefficient as drastically as what we would have gotten with a ratio. So I think this is one way to justify that the way we take the ratio as well as picking this oracle is to, in one way, make our life easier to really make the efficiency robustness trade-off to show up in the proposed estimator. So of course, if there's a, I guess, better justification for relative to the oracle, we would want to incorporate that in the paper. And so far, I think it would look like as if the each of the bias spaces is because we cannot pinpoint the exact bias, but rather have potentially a rough idea that the prior for the bias should be supported on a region. And in that case, if we can justify the oracle that way, then this would be the natural reference point. So yeah, so firstly, doing a ratio instead of taking the difference helps us really illustrate the trade-off. And secondly, focusing on the minimax risk here is how we think would capture if there is any information to be used on the bias, it's really the bound, not the exact bias that we can leverage.
Can I ask something related? In the literature review session at the very beginning, you mentioned that this kind of adaptive estimation have this near minimax property that is close to the oracle, I guess, compared to the oracle. That is really desirable, really nice property coming out of this whole procedure, right? So I guess that would be the way to justify why would want to construct this ratio in that way. Do you mind elaborate a bit more on in what sense this is like close to the oracle? or near minimax in some sense?
So near minimax means that the worst case adaptation regret would be close to 1 here. So this is because we take the ratio. So the best thing we can do is being as close to 1 as possible. This is also the same concept from high-dimensional sets about loss of efficiency under adapting to different parameter spaces. So in our situation, actually, as I have this plot here, only for a moderate range of the correlation coefficient, we can say it's close to near minimax. But this is again showing that sometimes it's not possible to achieve the efficiency robustness trade-off that easily as reflected in growing adaptation regrets as a function of the correlation coefficient. So yeah, the smallest it can get is 1, and if it's close to 1, then it's very close to the it will have a risk function that's very close to the oracle, but otherwise it would always be a little bit above.
Okay, so if there are no more questions, maybe we can wrap up and thank again Sophie and the 3 panelists for excellent job and questions.
Yeah, thank you so much for all these questions. I think these are very helpful for us to refine our arguments.